This video looks at exponentials. In particular, we're going to look at index laws, and then we'll do some exponential graphing as well. So starting off with the index laws. So a squared times a cubed. Index law 1 tells us that timesing will turn into adding. So this becomes a to the power of 2 plus 3, or in other words, that is just a to the power of 5. B squared over b to the 5, so that will become b to the power of 2 take 5, which is another way of writing b to the power of minus 3. One other way you can actually look at this is you can look at b squared over b to the 5. And you can actually imagine it like this. So you got b times b over b times b times b times b times b. And what do you know? The two b's on the top will cancel off with 2 on the bottom. So you'd be left with 1 over the top and b cubed over the bottom. Now you might be wondering, are these two things here equivalent? It turns out that yes, those two things are equal, and that is another one of our index laws. It's actually this one right here, number 7. Okay, if we have something like c root c and we want to write it without any square roots, you can think of this as c to the 1 times c to the half, and then index law 1 tells us that is c to the 1.5. We just add those together. So getting half there, that's because it's the square root of c, and that would be the last index law there. Moving on, 2x to the power of minus 3, just writing it without negative powers, you would keep 2 over the top, and you would have x cubed over the bottom. Simplifying something like this one here, just be sure that you are squaring the 3 as well as squaring the x. So you've got to do it to both things. Now that might seem really obvious when I'm doing it there, but if you're doing this with algebra and simplifying, it can be easy to forget this step in the process. Something like that is something we can do with index laws. So I'm going to leave squaring it till the very end, but we'll do with our numbers first. So we've got 2 over 4 here, which can simplify down to essentially 1 over 2, but I might not bother writing the 1 in there up the top. Then we've got c cubed over root c. So if we think about this, this will be 3 take away 0.5. So that would be 2.5 that we're left with, and we'll put it up the top there. Next we have d to the minus 6, and then we're going to be taking away another 1. So that'll give us essentially d to the power of minus 7. But rather than writing d to the minus 7 up there, I'm actually just going to write it on the bottom there as positive 7. So that would be me using index law number 7 here. Basically, if I have something like 2 to the minus 3, that would be 1 over 2 cubed there. I can flip it onto the bottom. But if I had something like 1 over 3 to the minus 8, I can actually move that back up to the top, and it will become 3 to the 8 up the top. So pretty much a negative sign means that you can move it up or down on a fraction and then make that negative positive again. Anyway, moving on. So we've got this situation here now. Now we need to do is square everything. So you'll double the power there to get c to the 5. On there, you're going to get 2 squared over the bottom, which is 4. And then d to the power of 14, because you're doubling 7. So in particular, if you think about something like a cubed squared, that rule would be a to the power of 3 times 2, which is a to the 6. So it's a rule like that that I'm using to deal with those powers in there. All right, next one we have. This horrible messy thing, all to the power of 0, is just 1. Because anything to the power of 0 is 1. The only little nuance here is I would have to make sure that c does not equal 0 and d does not equal 0 there. Otherwise you're sort of like dividing by 0 and it gets a bit messy. Technically here I'd also want to specify the same thing, so c can't be 0 and d can't be 0. Just got to be careful with 0, especially if it's on the bottom of a fraction, and especially if you end up with something like 0 to the power of 0. That makes us very unhappy. It's actually undefined. Alright, something like e squared times e cubed is e to the 5. Now in this case, e is a number because we're talking about exponentials. So the number e you can get on your calculator by doing e to the 1. It's about 2.718. Goes on forever, does not repeat itself. It's sort of like pi in that sense. And our answer there that we just had for e to the power of 5, not that it really matters what that number is, but you can work it out if needed. So e to the power of 5 is about 148. All right, now we'll look at graphing exponentials. Okay, now this is some real world data that I've collected of a cup of coffee cooling over time. And you can see that it sort of goes down like that. Generally, we like an exponential graph to look like a times b to the power of x. And occasionally what we can do is we can add on some height adjustment c. Now, if you want to get really, really fancy, you can also add on a horizontal adjustment c there and then I might call my height adjustment D. In our case, we're not going to adjust it horizontally at all there, so C would be 0. And just to simplify things a bit, I might not even talk about C in this model here. So let's talk about what A, B, and D do. A determines sort of where it starts. So if I look at that and I change A, that's actually going to be like a vertical stretch. We call that a vertical dilation. Now the D value will move it sort of up and down. So that's what we'd call a vertical translation. You're translating it up and down. And B is going to sort of change the shape of the graph a little bit and determine how quickly it's decreasing. B is the messier one to deal with. Now, if you want to interpret this in like real world terms, if I set B equal to something a little bit higher, let's say 0.9, and we're talking about exponential decay, basically every minute I'm going to have 90% of what I had in the previous minute. So that's what the B being 0.9 means. Now, if I set D just equal to 0 there, then the A value is actually going to be the starting point. So for example, I could set A equal to 65 right away to pretty much perfectly match the shape of that graph. And then I could set B to something a little bit higher to maybe make it match a bit closer. Even something like that would be a pretty good fit. Now this graph here is not at all realistic because a cup of coffee does not cool down to like 4 degrees. It will cool down to room temperature. So this is what the D height adjustment thing sort of does. If I set that to like a room temperature of 25, you can see that as this graph goes on, it will only ever go down to 25, something like that. So 25 might be an appropriate room temperature for this graph. I can then adjust A back. So if I want it to start at 65, then whatever A plus D is should give me 65. So I believe 30 should be the correct answer for that. Or I can't do maths, 40. And then B can adjust accordingly. So we can just try and mess with our B value here until we get something that looks good. Something like 0.97 could look pretty nice. Although whenever you're fitting a model, a good rule of thumb is to have the same number of dots underneath the line as you do above the line. So maybe I could make my B value a little bit lower just to accommodate for that. Maybe a tiny bit lower still. And that looks like a pretty good fit for our model. There we go. Now, one thing that I should mention is that, well, you can horizontally translate it. So if I went take 10, that would shift the entire graph 10 spots to the right. And that's what I was calling the C value before. The other thing to mention is that when we do derivatives, this thing here is kind of difficult to do a derivative of. It's definitely possible, it's just a bit messy. What we tend to do is use models which look like this. We use E as the base, and just the way that it works out, E tends to be a really good number for a base in the model. So I might actually try and use different letters, so maybe we'll just use G there, for example. And we'll see if we can fit a similar model, but most of the letters behave the same way. So F here will still be our room temperature, so I'll set that to 25. And then we can sort of adjust the other letters to make everything work. So G here would be our vertical translation, so I think that should still be 40, and that should make everything fit. And then K will behave a bit like what our B value behaved like before. So if K was maybe negative there, then I'm starting to get the K. So let's try something like negative 0.05, and that's looking pretty good. And negative 0.02, 0.03, 0.04, maybe 0.035. Something like that is going to be a really good K value. So the two models that we have for this, one of them was 40 times e to the power of minus 0.035 x plus 25. So that was that blue line we created before. And the other one was quite similar, only we didn't use a base of e, we just used a number there, which was 0.966. And you can see that the purple line, and let's make this not black, let's make it orange. The purple line and the orange line are basically equivalent models there. It's just the purple one has a base of e, and this other one has a base of a different number. In general, we'll want to use more of the purple formulas in Year 12 methods. Now you might be wondering why these two models are actually equivalent, and the key is actually in index laws. So if we look at something like this, e to the power of minus 0.035x, we can use index laws to write that like e to the power of minus 0.035 to the power of x. And then in our calculator, we can work out what that thing is. So it's e all up to the power of minus 0.035, and we get this number, which is about 0.966. So roughly equals 0.966. And would you look at that? That number is exactly the same as what we had in the other model. So these two models are just different ways of talking about the same equation.